Welcome back to the next video about my electronic steering wheel / jog IP68 project. In the previous video we started to do some static and bending calculations for our assembly card here, link in this description. In this video we will just continue with that and hopefully make a little bit faster headway than previously. Enjoy! The first calculations I want to do in this video is about those two stops that keep our shaft inside the assembly. In the first video we measured here a pulling force of the wheel of maximum 150 newtons and a pushing force of a maximum of 100 newtons. Card here, link in the description. These forces will produce pressures on these ring-like surfaces here and here. And our job is to calculate how large we have to make these ring-like surfaces so the POM-C bearing, that's softer than the aluminum here, can withstand those pressures. For our calculation of the edge load here in the previous video, we used the ball indentation hardness of POM-C, which was fine because we were talking here about a very small area under pressure, just here at the front of the bearing. However, with our large, big ring-like areas, we are compressing on a much larger surface, and so we cannot use the ball indentation hardness. Instead we will be using the compressive strength, and that's supposed to be a small Greek sigma, okay, small Greek sigma, according to EN ISO 604. And that's measured as follows. You take a small block of your material, in our case POM-C, 10 by 10 by 10 millimeters, on a hard surface, and then you press down on it with some force. And as soon as that force compressed the whole thing by 1%, there are different measurements for different percentages here, but we take the 1% measurement. So we compressed that by 0.1 millimeters. You simply take the force and divide that by your surface here, and that's 10 by 10 millimeters, so 100 square millimeters. And that gives you your compressive strength. And for POM-C, or for 1% compression, that's 20 megapascals. And I mentioned it often enough, Newton per square millimeter is megapascal. And how do we calculate the actual pressure on our stops? As I mentioned, we have some ring-like surfaces, and to calculate the area of such a ring, you simply take the area of the outer diameter circle minus the area of the inner diameter circle. And if you rearrange that a little bit, you come to that formula. So pi over 4 times, in brackets, outer diameter squared minus inner diameter squared. And then to get the pressure, you simply divide the applied forces, in our cases 100 newtons, respectively 150 newtons, by the area. Time to make another Excel sheet. But before we have a look at that, we have to decide what's an acceptable pressure here. I mean, the compressive strength is 20 megapascals, meaning that 10 by 10 by 10 block is compressed 1% or 0.1 millimeter. But in a linear approximation, that means if that block would have a height of 20 millimeters, we would have a compression of also 1%, but 0.2 millimeters. And I'm arbitrarily setting here the limit for compression at 0.1 millimeter. as always. Our front extension here of our bearing for compliance reasons to take up the edge loading is about 20 millimeters wide. So yeah, we have to halve here the acceptable pressure if we want to stay within 0.1 millimeters, assuming this is really rigid back here where it's mounted. And on the other side, we have 150 newtons. That doesn't matter. We will calculate the pressure. But this is much longer. So let's say at least 5 centimeters. So we can here only apply a maximum pressure of 200 megapascals divided by 5, so 4 megapascals. I have two different tables here. One for pushing onto the wheel, so for our front stop, and one for pulling on the wheel, so for our stop at the end of the bearing. And I did the calculations for different inner diameters, so shaft diameters between 12 and 60 millimeters, and then an outer diameter of our stop between 14 and 24 millimeters. And as we just discussed, the limit here for the pressure for the push force is 10 megapascals. So the 20 megapascal compressive force of POM times the 10 millimeter where it's tested divided by 20 millimeter. That's the length of our extension there. And here analog it's 4 megapascals. And as you can see, but maybe for that case here, it doesn't really matter. We are golden. The pressures are all well below our limits. Now, what about the bending of the bearing itself? We have to look at this in two parts. First, our little extension here at the front and then the main body. Remember, we extended the bearing here in the front to make it a little bit softer. We've done that to mitigate the effects of edge loading we get here at the end of the bearing when our shaft is actually bending from a load. So we want a contact surface of at least 1 millimeter here. And the total bending of the shaft over its whole length is about 0.1 millimeters, give and take, depends on how our final dimensions are. So I want that extension here of the bearing to bend at a given force at least 0.1 millimeter on that short distance. And this should give us here enough contact surface. We already calculated the force that is acting here on the shaft, respectively the edge of the bearing, several times in several formats. And we can assume that this stick out here, not that stick out of the shaft, but this extension of the bearing is about 2 centimeters long. So we will calculate that like we calculated the bending of the stick out. So we will assume that this part here is basically fixed and doesn't move, and we just have our front force applied here. And we will use the trusty online calculator for that. So that's our case. We have a front clamping here. Then we have here our bearing with the length L and then our force here. The length is only 2 centimeters and the force, one of them was 360 newtons. And now we don't have a solid shaft, but for the stick out or for the extension of the bearing, I go for a pipe-like shape with an inner diameter and an outer diameter. And our inner diameter, I start with 12 millimeters, so for a 12 millimeter shaft, and an outer diameter of 20 millimeters. And so you see our maximum deflection is, yeah, very low. That's because I'm still here on aluminum. Now, the modulus of elasticity, you remember these formulas for POM, is not 70,000 megapascals. It's actually only 2,500 megapascals. So let's do that calculation again and have a look-see. Oh, yeah, and much more deflection, 0.06 millimeters, but that's still not enough. That's still too hard for that case. So let's go down to 18 millimeters and recalculate that. And now we are spot on. Okay, well, 0.09 millimeters. Yeah, we could even make that a little bit softer, but I won't bore you with all that stuff. I do some calculations and make a nice table again, and then I come back to you. And here are the results. I did the calculations for two different cases. First, for a front force on the bearing of 360 newtons, which corresponds to a stick out of 5 centimeters and a total bearing length of 7 centimeters. Yeah, we did all these calculations before in part 1. And then for 385 newtons, also stick out 5 centimeters, but total bearing length only 6 centimeters. And then we have two different shaft diameters, so our inner diameter of the bearing, 12 and 14 centimeters, and then the outer diameter just here of our bearing extension between 16 and 20 millimeters. And you see I have here windows which are in an acceptable range. Of course, if I hit exactly 0.1 millimeters, we are golden, that's what we wanted. But I think plus minus 20%, so between 0.12 and 0.08 millimeters would also be acceptable deflection range. Everything what's beyond is not acceptable. It's either too hard, too stiff, not complying enough to our shaft, or it's too soft. And that's something new. We have now here just a window. So, for example, for our 12 millimeter shaft here between 70 millimeters and 18 millimeters outer diameter of that bearing extension. And that's a problem. Because in the previous step, we did those calculations here about the pressure our stop here would exert at the end of our bearing for axial forces. And there clearly the bigger the outer diameter here of our bearing, the bigger, that is, the lower the pressure. However, now we have to stick here between a very narrow window, which is more, to the critical side here of our values. We said these values are all acceptable. But we got more safety margin if you have a larger outer diameter, and our safety margin shrinks when the outer diameter goes down. So here we again have two parameters in our construction which are competing against each other. But now let's calculate the required diameter or dimension of our main bearing body. And the principle is here the same. We assume that it's firmly clamped in here by whatever we attach the bearing to. And we have a force exerted here at the end. Now, I think we never ever actually calculated that force. It's because it's smaller than the force here at the front. But anyway, you do hopefully remember that the deflection increases with the length cubed, in part 1. And that the force at the back of our bearing is simply the stick out of our bearing times the force applied here, our 210 newtons, divided by the total length of our bearing. Also shown in part 1 of the static calculations. We're back in our beam calculator. The same case, so firm clamping, length out here of our beam and a force applied here. Other dimensions now and other forces. So the length here is, in my initial calculation, 6 centimeters. That's our minimum bearing length we fuddled around with for the last few cases. And the force here is 175 newtons. Remember, radial force maximum at the wheel in the front on the 5 centimeter stick out is 210 newtons. So 210 newtons times 5 centimeters divided by the 6 centimeters of the bearing. That's 175 newtons. And then further down, my bearing main housing will probably be quadratic or rectangular. And we start here with something 25 by 25 millimeters and a 12 millimeter hole for 12 millimeter shaft. And you see I have here now a deflection of 0.15 millimeters, well, 0.16 millimeters. In fact, that's too much. Again, I will play around a little bit and come back with a table to you. I didn't even bother to make a nice Excel table because turns out that's completely uncritical. So I already did that calculation for a bearing length of 6 centimeters, stick out 5 centimeters. We have a force of 175 newtons. And for an inner diameter, that is shaft diameter of 12 millimeters and a width, quadratic of my whole bearing, I get a deflection of 25 millimeters, I get a deflection of 0.16 millimeters, which is too much. But if I go up to 30 millimeters, deflection is down to 0.08 millimeters, which is fine. And it's the same for an inner diameter, shaft diameter of 40 millimeters. For a bearing length of 7 centimeters, the force is reduced to 150 newtons. But remember, deflection is linear with the force, but cubed with the length. So there, with a 12 millimeter shaft in the middle and a width all around of 25 millimeters, we get 0.22 millimeter deflection. But if I go up to the width to 30 millimeters, we are also down to 0.1 millimeters. And the same for a 14 millimeter shaft. Now you might wonder, why isn't there a noticeable difference, at least if you go to a hundredths of a millimeter, between a 12 and a 14 millimeter shaft? And the reason is, if you bend such a hollow beam, the brunt of the force is taken up by the outside material. Here in that bending direction, this outside stuff is stretched a whole lot. And that outside stuff here is compressed a whole lot. While, the inner part here experiences much less compression and stretching and therefore much less forces, and therefore it contributes only very little to the total stiffness of the bearing. That's it for today. I know, a little bit shorter video this week, but we had some quite long videos in the previous weeks. Anyway, I also need to step back now and get all these different requirements for length and thicknesses somehow together without any contradictions and make an initial drawing. And as soon as I'm done with that, I guess I come back to you and we talk about the whole thing a little bit more. Till then, bye.